So now we know how to use the law of sines when we know any two angles and any side length. So for example, if we knew alpha, beta, and A, we could figure out B. We could also figure out gamma because we know that the sum of the angles is 180 degrees, and then we could figure out what C is. Do keep in mind that if you're given the information such as alpha, beta, and C, it might initially look like you cannot use the law of sines because it looks in this case that every law of sines has two unknowns. For example, sine beta over B equals sine gamma over C has two unknowns, but really gamma is an unknown because you can add up the three angles to get 180 degrees and determine what gamma is. So now that we've discussed how to determine or how to use the law of sines when you're given two angles and a side length, we're going to discuss how to use the law of sines when you're given an angle and two side lengths. And the situation is a little bit more complicated here because let's imagine that we knew this information that I've circled. So we could solve for beta in the following way. We could multiply by b and we get that sine of beta is b times sine alpha over a. So we need to solve for beta when sine of beta is b sine alpha over a. Here there is a subtle detail that we need to talk about before we can go on to this type of law of sines problem. And we're going to talk about this now. The detail that we need to talk about is we need to discuss how to find all solutions to sine alpha equals a number. So if you look back here, remember, if we knew alpha, a, and b, then this here, this quantity on the right-hand side would be known. It would be some number. So we need to know how to solve sine beta equals some number. And so I'm going to show you how to do this in an example, although I've called the angle alpha, with the restriction that alpha has to be between 0 and 180 degrees. And this has to be true since alpha is an angle in a triangle. And when I say it has to be true, I mean that it has to be true in the cases that we're going to examine with the law of sines. You could certainly talk about how do you find all solutions to sine alpha equals 0.3 without this restriction that alpha has to be between 0 and 180 degrees. However, since when we go to use this in the law of sines, the alpha that we solve for has to be between 0 and 180 degrees because it is the angle in some triangle, and an angle in a triangle cannot be larger than 180 degrees. So let's see what the subtle point is here that you'll need to remember. So I need to solve sine alpha equal 0.3. Now previously we talked about the inverse sine function, and we can rewrite this in terms of the inverse sine function in order to find a solution. So if sine alpha is 0.3, if you rewrite this in terms of the inverse sine function, then this means that alpha is equal to sine inverse of 0.3. And remember the domain restriction, this alpha is going to be between minus pi over 2 and pi over 2. And in terms of degrees, that will be between 90 degrees, negative 90 degrees, and positive 90 degrees. Now this absolutely will give you a solution. You can go ahead and use a calculator to evaluate what this alpha is. Sine inverse of 0.3, make sure that your calculator is in degree mode if you're working in degrees. And we get that alpha is 17.45 degrees. Let's round to the nearest 1,000th, 17.458 degrees. However, there is another solution. Because there is another solution, I'm going to mark this as alpha 1. So keep in mind that this gives you a solution between negative 90 degrees and 90 degrees. However, we're looking for all the solutions between 0 and 180 degrees. So in order to convince you that there is another solution, let's look at the unit circle. So we'll draw some axes. Here's a reasonable circle. And now we found this alpha 1, which is about 17 degrees, such that sine of alpha 1 is 0.3. And what that means in terms of the unit circle is that we found an angle in the first quadrant. I know it's in the first quadrant because my alpha that I solved for using the inverse trigonometric function, this alpha has to be between negative 90 degrees and 90 degrees, which tells me that it has to be in either quadrant 1 or quadrant 4. Those are the only two possibilities because that's where negative 90 degrees and 90 degrees are. And I know it can't be quadrant 4 because sine of alpha is positive, which means the y-coordinate where we have an intersection with the unit circle is positive, so it could not be quadrant 4. So here's a depiction of alpha 1, and this terminal point here where you intersect the unit circle is going to have some x-coordinate and the y-coordinate will be 0.3. Now if you find another angle between 0 and 180 degrees, so between the positive x-axis and the negative x-axis, that when it intersects the unit circle has the same y-coordinate, then sine of that angle will be also 0.3. So if I draw a horizontal line here, like this, then where my horizontal line intersects the unit circle, so right there, the y-coordinate of that point that I've drawn is on the unit circle, and it has a y value of 0.3. So this other angle that I'm going to draw also has a sine of 0.3. So let me label it. So let's call this alpha 2. And what I'm saying here is that sine of alpha 2 is also 0.3. So let's recap so far. So we wanted to find all the solutions of sine of alpha equals 0.3, but our alpha needs to be between 0 and 180 degrees. We used the inverse trigonometric function, sine inverse, in order to find one solution, and that solution was in quadrant 1. However, there's this other solution, alpha 2, which is in quadrant 2, which also has a sine value of 0.3. Now, what is alpha 2? I've said that there's this alpha 2 that has sine of alpha 2 equals 0.3. How do I figure out what it is? Well, if you look at my drawing long enough, then it would become clear to you that the reference angle for alpha 2 is alpha 1. And so if you go around by alpha 2 and then go a little bit more by alpha 1, the reference angle, you get to 180 degrees. So alpha 2 plus alpha 1 equals 180 degrees. And now you can use this equation to obtain what alpha 1 is, or excuse me, what alpha 2 is. So alpha 2 is 180 degrees minus alpha 1, and alpha 1, that was 17.458. And so my second solution is 162.542. And with the caveat again that this is an approximation because I'm rounding. So going forward, you should know that when you need to solve sine of some angle, I'm going to put beta here to make sure you all understand it doesn't necessarily need to be called alpha, equals some number between 0 and 1. And let's just give that a symbol. Let's call it a number sign. When you need to do this, there are two solutions. There's the first one, which you can get via the inverse sine function, sine inverse of whatever number is on the right-hand side. That's going to give you a beta 1 that is between 0 and 90 degrees. But then there's another solution here, this beta 2, which is 180 degrees minus beta 1. And this here, remember, comes from the fact that you have this drawing which indicates that there's a solution in the second quadrant with reference angle alpha 1, or if you're using betas, beta 1. So for example, if you're working a problem and you need to solve sine of gamma equals 0.5 with gamma between 0 and 180 degrees, then you're going to get two solutions, gamma 1, which is the inverse sine of 0.5. 0.5 is 1/2, and the inverse sine of 1/2 is 30 degrees. That's one of the special angles. And then you're going to get a second solution, gamma 2, which is 180 degrees minus 30 degrees, which is 150 degrees. And now I think the last point that I need to make is occasionally you'll come across situations where you have to solve sine alpha equals some number which is larger than 1. Let's say 1.1. If you ever, and I guess alpha is going to be between 0 and 180 degrees again, so let's write that. If you ever come across this situation, then you may remember that this is going to have no solutions because the possible outputs of sine of alpha are all numbers between -1 and 1, and so this will have no solutions.